Welcome to the Microsoft Research Summit. This is a session on software productivity. I'm Neel Sundaresan. I'm the Vice President of Data and AI in the Developer Division of the Cloud and AI Division of Microsoft. So today I'm going to walk you through several generations of innovations and work in software productivity and what foundational elements contributed to these innovations. A lot of the stories I'm going to share, the concepts I'm going to share are through my own personal lens and my own personal journey, starting off as a compiler engineer to today introducing AI into developer productivity in the cloud world. So let's start at the beginning. When we think about automation, and when we think about automation through software, what is automation? Automation is basically taking mundane manual tasks and using computers to automate them. And this task could be like converting one form of data to another, or what I saw when I was learning computer science was a lot of converting a lot of programs in one language into another language, right? So there are a number of computer programming languages are invented, and this was a programming task. Now, if you had one program to translate, you could write a third program that translates from one to the other. But what if you had a lot of programs to translate from one source language to programs in target languages? Now, you could hire a programmer to translate each of these programs, but that would not be scalable and would not be smart. But you have compilers or code generators or transpilers, or call it depending upon the source and the target language. The source language could be a human language or a programming language. The target language could be an architecture language like machine language or another programming language, and so on. But instead of having all these programmers write programs for individual, translate individual code, you have compilers or these transpilers that will write, that is basically a program. You can have one programmer write one program that translates code in any one language into any other language. Now, what is the foundation of being able to do this? Because the source and the target language have grammars associated with them. So in this generation, the grammar was the foundation of innovation of developer productivity or software productivity. So let's go beyond what I just gave an example of a compiler. What if you had programs in many languages? So let's say there are M source languages and N target languages. Now, if you were to do it in the traditional way, you would land up writing M times N compilers or transpilers or translators, and that would be inefficient. But if you look at these programs, they have a general task. What is the task that they're doing? Their task is to take a program in one language and translate it to a program in another language. Now, the first level of innovation came about when we had retargetable compiler code generation. Now, what that meant, what you could do is you could have an intermediate language. Then you could write a bunch of translators going from the source language to the intermediate language. Then you have translators going from the intermediate language to the target language. So now what you've done is you've taken this job of writing N times M transformers to M plus N transformers. So that was a big innovation. And as new architectures were invented, as new programming languages invented, these tasks were automated that way. But you could go even a step further. Now, what is the task of actually translating it? So there is a source grammar and there is a target grammar. Now, the task is actually taking constructs in the source grammar or the source language and writing transformations for each of those constructs in the target language, which means there is a structure to these translators, which is basically transformation rules from source to target. Now, that itself is a language, which means that itself has a grammar associated with it. Because it has a grammar associated with it, you can actually write just the translation rules and write one computer program that drives through the translation rules and translates program in any given programming language to any other programming language. Now, if you take these programming languages, the transformation rules have a lot of similarities in them. So you can even think of taking it to the next step and automating the writing of the translator, the code generator part, where you could automatically generate the code generator. So there are multiple levels of innovations that could happen because of grammars. So the whole idea of this generation of innovation was, why write code when you can generate them? And what was essential for this? The notion of grammar, the schema was essential for this kind of automation. And there were cases where the grammar was absent. Then what you could do is you could use examples of programs in those languages and automatically generate those grammar or try to automatically generate those grammars. But these kinds of approaches worked only for small domain-specific languages like regular expressions. Now, what was a big miss, at least in my own personal experience, what was a big miss? I was writing these tools that could generate lots of code or translate millions of lines of code in one source language to target language. But what I didn't see is I didn't think of all of this code as data. Now, we were very driven by grammars, and we always worried about having good schema and writing good transformation rules. But we didn't think of all of these programs that were written and generated as data. But all of this was about to change because what happened? The internet came about. Now, with the internet, what happened? We got a ton of data. There was markup data, image data, textual data, and a lot of this data is for human consumption. If you look at commerce site, you have transactional data, you have behavioral data, etc. But what we lost in the process was schema or grammars, right? There was no grammar with it. But because we had so much data, the modern data science was born. The focus was on how to process the data, how to apply algorithms to this data, and how to solve new kinds of problems that could not have been solved before using this data. So I'm going to give you a few examples. Now, in this generation, as we see, data became the foundation of innovation for productivity. And there was a great paper written by folks at Google about the unreasonable effectiveness of data. And the paper said simple models can work better than with more data. So you don't really need complex models. A lot of the machine learning algorithms or the data science algorithms we did at that time were simple regression algorithms, feature-based or engineered features of simple number of features, but add more and more data to it to get effective solutions. I'm going to give you a few examples of that. For example, we built search engines and recommender systems just based upon volumes of data. And we could solve recommendation problems when users come to the website by looking at their data, see what next product are they going to buy based upon what they bought before, but when are they going to buy? So we could solve problems that are more human than the kind of problems we could solve before. Now, also data brought other fields like economics and other social science fields closer to computer science. The whole area of digital economics was born. We could answer questions using data like, what kind of strategies do people follow in online markets? Or we could say, what happens when we introduce internet sales tax? We could answer causation questions. We could answer counterfactual questions. We could answer elasticity questions. What if I increase the sales tax by 1%? What would happen? Right? We could say what could happen when new smartphones were introduced. How is it going to inform and evolve the way commerce is done? We could talk about badging and how reputations work on the internet, etc. And all of this was due to the effectiveness of data. And simple algorithm, simple statistical algorithm, but we could solve some real complex problems. And even if you look at things like computer vision and speech, we didn't really need complex algorithms. And up until that point, a lot of work in speech and vision were rule-based and used very small amount of data. But you could look at large amounts of data and look at their patterns and tease out elements of those patterns and just do science in them. We could build an entire vision search by just looking at the data and the elements of the colors in the data, etc., to figure out the style of the, let's say if it is a piece of clothing, the style of the clothing, the color of the clothing, the patterns of the clothing, etc. So the internet allowed us, and the data availability allowed us to build systems that were at scale, that could process data at scale and solve problems that were extremely data-driven, which was quite different from before. But again, things were about to change. With new hardware available, GPUs available, etc. And let's look at that third phase. Now, 6 years ago, I joined Microsoft, and a colleague of mine showed this picture to me, and this was a picture from the developer division. So now this audience of ours are developers who, we have an audience of about 20 plus million developers for whom we build tools, right? And the way we look at the software development cycle is there's an inner loop, which is where the developer writes code, debugs the code, and edits the code, and so on and so forth. And on the outer loop, which is basically more coarse-grained tasks like pushing it to production, running builds, bug patching, doing pull requests, documenting the code, testing the code, and doing CI/CD or continuous integration, etc. Now the question comes, can we automate this process? Or can you do things that will benefit the developer by building the right kind of tools for them? So again, coming with a data background, I was asking the question, what kind of data do we have? So if you look at the internet today, repositories like GitHub have tons and tons of data, code data. Even companies within themselves, inside of them, have tons of data in multiple languages. So we got a lot of code data. This is the first time that actually I saw code as data. And then there are a lot of tools like the canvases on which the developers write code, like VS Code, Visual Studio, notebooks, Azure Shells, etc. And there are user forums like Reddit and Stack Overflow and many other forums from which we can get data. So if we can take all of this interaction data, can we build interesting tools with this interaction data? That was the question that I wanted to answer. But I wanted to start small. So we wanted to start small. So what is the first thing we could do? Number one, first we need to know what can we do with this data. Can we build tools that address the needs of the large community of 20 plus million developers? And can we teach a machine, or can we build systems that can learn enough to automatically do stuff or assist developers to do the task with reasonable accuracy? And the third question was, can we do this over and over again? So can we teach the machine once and repeatedly use it to do many tasks? We know that it won't be perfect because a lot of the stuff this machine learns is probabilistic, but if we can build a system that's open to repair, then we can do very well. So basically the goal was to automate the mundane, because people make mistakes, engineers make mistakes doing mundane tasks, and when there are complex tasks that they can't keep in their head or in the system, can the machine assist with these complex tasks? So with this, the background, we started with a very simple goal. So if you look at developers writing code, about 30% of the code they write are API calls. And if you look at any kind of IntelliSense that most tools offer today, they offer IntelliSense where the call is listed either in alphabetical order or frequency order. So we asked the question, can we do something better, right? So which means I'm in a certain section of my code, I've written a bunch of code before, and I'm going to continue writing. What is the call I should make at this point of time? So a simple thing to do is take all the programs and build flow graphs out of them. And once you have the flow graphs, you can use ML to say what call would follow what call, right? So you build a simple Markov model, Markov chain model, and answer the question of, given a package, I made call A, or I've not made any call at all, what call would be the next call I would make, and make a suggestion. Now, this was a very naive, but at the same time, useful thing to do. When we shipped this, the developers were super impressed with this. They were very happy that we provided them a tool that was more intelligent than what they were used to. And this is an unusual experience for machine learning folks, because typically when we build models, they work really well offline, and when we bring them online, the performance is much lower. Here we saw with user feedback, actually the users were a lot more happier. So with that, at that time, we thought maybe we could do more. And the reason is that with this kind of a model, the model was not scalable. It was not scalable because for every package, every class, you have to build this chain. So we went with a sequence-to-sequence deep learning model and improved the performance. In the sense, it could get more coverage and it could make better recommendations, but the model was a lot larger. And then we have challenges when we deploy these models into production. So we had to do a whole bunch of other engineering things to make sure that they work well. Now, right around this time, great innovations were happening in the AI area, right? Great innovation in the hardware. We're getting much better hardware with the GPUs and so on, much better algorithms in deep learning, and great ways to process data. Now, what we saw that from these models that were built out of these, the combination of these things really powered the early NLP work in the last 5 years. The Elmo and BERT, which are not as big models as we see today, basically changed the foundation of NLP research was done, right? And then more recently, models like Megatron and then GPT-3 and T5 are even more larger and even more complex and even more generalized. And the nice thing about these systems are that you don't need to now do any more task-specific features when we deploy these models. Now, also, they consume extensive volumes of data they tend to have general intelligence. So they have generally AI intelligence, and they can be easily adapted as well. So now the theory is that now because they have the general intelligence, we can do some slight tweaks in the downstream tasks that we might want to solve. And these downstream tasks can be solved either through the conversation with the systems, if the systems are large, or just by fine-tuning. So there are a lot of opportunities related to this AI revolution that we can apply to developer productivity. So we come to the third phase of what is offered to us as foundation. Now we have AI models as foundation, this third generation. Right? So what are the opportunities here? Now we have the ability to capture the universe of domain information. So think about all programs ever written, all images ever seen, all videos ever created, and what kind of intelligence can you gain by mining them and building models on top of them. It has the capability to learn from different modalities. You can have text and images, or text and programs, and so on. You can mix and match them and have higher intelligence on top of it. Then you can encode this language in high volume in higher dimensional forms. And you can express this knowledge in a way that you can adapt to specific tasks. So if you ask the machine, what have you learned? We really don't want to know what the machine has learned, but we can adapt whatever it might know for a specific task that you might want to do. And then you can extend this knowledge either through conversation with the machine or by tuning it to achieve these specific tasks. I'm going to give you some examples of these. Right? But there are some practical questions that arise. Right? Is the machine learning something, or is it just memorizing? Has it seen everything that has ever been to see? So for example, if I push all the programs that I've gained off of the internet through this machine, or if I've seen all the text I've seen on the internet through this machine, has it seen everything that is there to see? And the next thing that one writes, whether it's code or whether it's text, is just going to be a combination of the parameters of what it has already seen. Or does it even matter, right? That it has seen everything or it has not seen everything at all. So there is some confusion here that is it intelligence or is it knowledge, right? Or does it even matter? Now the bigger question is, will you trust what it does? Will you trust what it does because, what is the cost of being wrong? When it's right, you're happy. When it's wrong, how much is it going to cost you depending upon the task you apply it for. Then when we go into practical systems for deploying these models, you ask the question, what are the training costs? How big a hardware do I need? How much energy does it consume? What are the costs for inference? Who's going to pay for it? Are my customers going to pay for it? Am I going to pay for it? What's the ROI on this kind of inference cost? And what are the scaling costs, right? If I want to deploy to a large number of users or solve larger problems, what is it going to cost me? What are the deployment costs? So these are questions we often ask in product groups. Then we have other questions about the data and the models. How good is the data? What is the quality of the data? What kind of biases do you see? Pretty much any data that you gather at large scale, it has this zip property where you've got a heavy head and a long tail. Right? If you get all the text on the internet, quite likely most of them would be English. But if you see these smaller languages, smaller tribal languages, we'll almost see no examples of that. If you take all the code on the internet, quite likely you will see popular languages show up a lot, and the less popular languages will have very few examples of that. Does that bias the decision that you make off of this machine? And what about privacy? What if people have put in information in there that the machine is smart enough to violate their privacy? What about security? Can people inject bad code into the system so that it produces insecure code? And who owns all of this data, right? If I write code and put it on the internet, do I own it? Does that machine have the authority to take it and interpret and do something with it? And because these models are big, because these AI models are very, very big, they tend to be less transparent, right? So they're not able to explain what they do, what decision they make, and why they make the decision. So how much do I trust this decision? And again, the question becomes, is it just parroting or learning? Is it able to extrapolate? So for example, if it can help me with today's situation, if the situation changes tomorrow, right? Think of an AI system that's giving guidance for a cure for a disease. What if the virus has multiplied or a new kind of disease has come about? Is it going to be able to help me? Can it extrapolate itself? So these are all questions that come up when we look at these large systems that you know less about. And coming back to our own system, our own area where we deploy products for our developers, number one, we are kind of incorporating these into existing products that have existed for over 20 years ago. So we have to replace existing pieces of existing code with these models. And what are these models? These models are just matrix forms. So how do I replace code with, say, stochastic gradient descent? And there is this whole idea of software 2.0 that Andres Karpathy wrote about a little while ago. And so we need to kind of re-architect some of these systems to incorporate these models into these systems. We had other kind of challenges. The model footprint on the edge has to be less than 30 megabytes. And that's a lot less than what the default models we produce were. And how does it interfere with the user experience? And typical development process is an analytical process. So if you interfere with the user experience, even if you make a good recommendation, the developer may not like it, right? And the response time is equally important, right? Because somebody's typing away, and if the system pops up and makes a recommendation, it cannot take more time than that is visible to the developer. And then there's a lot of privacy constraints as well. If I'm an enterprise, I may not share my data with the system. So how do the system provide a client-only model, right? I may not want to share my data. I want to keep my data private, and I need a model that works for myself. So there are a lot of these questions that have to be answered that are way beyond just having a smart algorithm that will do wonderful things for you. Right? We have to honor privacy, we have to honor security, and we have to protect from the rogues that could poison our AI system by injecting bad code into the ecosystem. So with that, we basically in mind, we built a transformer model. Again, what is it? The simple kind of transformer is a generator model, which is you're writing some text or you're writing some code, and the job is to predict the next token, right? So for example, if you're typing out an Outlook or a Gmail, when you're typing out text, you see this recommendation that comes up saying you're likely to type this text. That's a kind of recommendation. And in case of code, all we had to do was, what is the next token or the next sequence of tokens you would type, predict it, and be as right as possible. So what we had, our first model was a generator-based transformer model, which was a GPT model, unlike the BERT model that was used in the NLP community. Now, when we deployed, there's a lot of lessons learned. Like we hit the limits of data parallelism. We need to figure out how to incorporate model and pipeline parallelism. In order to fit the model into the client, we needed to quantize them. We need to do 16-bit and int8 arithmetic. We need to distill the model by removing layers, by building small student networks out of the large models, right? And we need to take advantage of the parallelism, the SIMD parallelism that was available on the CPU, right? We had to do other kinds of engineering tricks, like caching values from the client, and we had to do innovations in beam search and sampling for faster inference and better recommendations. So these were things that you had to do to push it to production, make the developer happy, and make it work, right? So, with this in mind, we kind of said, okay, we got one thing right. So can we do other software engineering tasks? So one thing is we're going to focus only on software engineering tasks. And can we achieve multiple software engineering tasks with minimal amount of pre-training costs? Which means when we build these foundational models, it needs to be know only about things that are related to software engineering. That could be text, that could be code, that could be documentation related to software. And we want to reuse these models, and we want to reuse the data for new kinds of tasks as well. And we want significant flexibility in fine-tuning and inferencing of these models. And we also want to enable innovation in software engineering. So that's one of the wonderful things about this, is that if you can create a system that, because we can come up with only so many innovations, but we put it out to the community, can the community innovate on top of it? So these were some of the goals that we had. And with that in mind, with the flexibility and the efficiency that we wanted to create for our ecosystem, we designed our system to have a certain architecture. So these systems don't compare in scale to, say, GPT-3 or something. And typical models are about 1 billion parameters. But what it has is an architecture that is super flexible. So contained inside the architecture is an encoder kind of architecture, which is basically a BERT architecture commonly used in NLP tasks. It has a GPT architecture, which we saw for code recommendation in the first example. And so we could do things like code completion, we could do code quality classification, etc. Then it also has an encoder-decoder, about sequence-to-sequence model that allows you to do tasks like translation or bug patching or unit test generation, etc. So we wanted to create an architecture that's flexible enough to fine-tune for tasks that are relevant to software engineering and can also add more tasks as well. Another thing that separates this from, say, what you see in the typical NLP community, where they use metrics like the NLP metrics is it's not just how close it is to the word, not at a distance, right? It's beyond that. How good is the program that you generated? How efficient is the program that you generated? So we have our own metrics called the plum metrics in order to do that. And then, making this package available to be deployed using, say, Azure or a cloud platform into production, and also have layers of dogfooding, trying it out, trying the model offline before we can push it to production. So this is kind of the general architecture of the system that we built. It's called DeepDev. It's available on deepdev.microsoft.com, so you can sign up, download, and build your own fine-tuned tasks. And it's trained on all kinds of code and documentation and text data. So I'm going to give you a few examples of how we use this to do other software engineering tasks. So one example would be, how can we generate whole methods from specifications? So the specifications could be just function signatures or text or doc strings. And so this uses a encoder-decoder model, sequence-to-sequence model that basically translates from one to the other. I'm not going to go into the details of it. It's very well written in the paper, described, and our results basically, number one, showed that we at this scale of parameters, we can't use a GPT model. We need a sequence-to-sequence kind of model. And then the second thing we learned was we needed really the program language understanding metric. We can't just use the standard blue metrics or perplexity metrics that is used in NLP, right? Because we want to answer questions like how good is the generated code, how syntactically correct is it, what are the semantics, is it executable, is it efficient, and so on and so forth. Another example would be a transpiler, which basically says, I've got code written in one language. I want to translate. This is very similar to the example I started my talk with. I want to generate code written in another language. Can I do that for free? How do I do that, right? Quite often, programmers, when they write code, they are looking for an API call. They want to know how to do, let's say, write a certain algorithm or call a certain API. And sometimes this API may be available in one language, but that may not be the language in which the program is programming. So in which case, you might want to do combined search with translation as well. Here, I'm going to talk only about translation. So this, again, uses the sequence-to-sequence model of the DeepDev platform that we have. But during fine-tuning, it does some clever things, right? Number one, you need parallel data. Now, what is parallel data? You need examples of code that are equivalent in two languages. So let's say I'm translating here in this example, Python to C++. I need examples of Python code that's equivalent to C++ code. So this is one of the things that we feed into the system when we do the fine-tuning. And this is collected from sources where, if you have examples of assignments or competition where, a certain task is done in multiple languages. So we mine these examples, we curate them, and we produce equivalent examples for the same task, and then put that into the data set that's used for fine-tuning. Another thing we do is that we do back translation, which means if you're going from Python to C# or C++, we go from C++ to Python as well, and we do kind of iterative training. Again, the details, I'm going to skip it to the paper, but what we found by doing all this and using the foundational architecture of DeepDev, we could get pretty good accuracy of translation of Java to C# and C# to Java. I'm going to give you another example here is, unit test generation is a big task. Developers spend about 30% of the time writing unit tests for the code they write. It's an important part of our software engineering process. So the idea here was, can we generate high quality unit tests for the code that was written, for any piece of software that's written? So again, using the model as a platform, we use the encoder-decoder part of the system, and for fine-tuning, we use the context of the method for which we call the focal method. So the method for which we want to generate the test code, and incorporate things like the fields in the class, the constructor of the class, etc., and generate automatic test code. So here's an example here. There's a function called createFloat, and by running it through the system, it generates test examples. It basically generates two assert statements instead of that. And the way we measure the goodness of these metrics is, or this translation, the test generation is how readable is it when it generated it, and what kind of test coverage does it provide to the system. So these are the metrics of goodness when we use a system for automatic unit test generation. So one of the things through the journey of doing all of this stuff is we found that offline metric is very different from online metric, and which is also very, very different from user metrics. For example, offline metrics just provides us with a baseline metric to qualify for the next step. Now, dogfooding helps us further to strengthen our trust in the models, and basically helps us, we talk to a handful of developers, they try it out, we look at what does their experience match with their offline metric. And then when we deploy it, we typically tend to see much poorer scores in terms of the metrics, that whatever metrics we might have. But at the same time, when we do user surveys, we kind of learn about how much user experience interferes with the user's behavior, and complements or actually reduces the quality of the metrics provided with the algorithms. So we believe that user experience plays a huge role in bridging the gap between user expectation and the goodness of the algorithm. And we try hard, in all of these models, when we deploy them into production, user experience is not talked about enough when we read papers in AI, but it's a very important part of the system when we deploy these AI models into production. So in summary, we found 3 foundational entities that have helped us with innovation in this space. Now, first, there was grammars that I described. The use of grammars effectively made automation possible through code generator generators, and translator generators, and so on, where significantly less code had to be written and code is generated instead of being written. And then came the big wave of big data. Big data allowed us to create data-driven products with reasonably simple algorithms by taking advantage of the volume of the data. And we could reduce information friction, we could create data-driven products and answer questions about causality, incentives, and user behavior. And now we are in the golden age of AI, where we see huge innovations in GPU hardware, in data processing, as well as deep learning algorithms. And this has helped us build AI platform systems like DeepDev I described, with reasonable intelligence about a particular domain. In this case, we are talking about software engineering as a domain. And by using these foundational platforms that has a reasonable intelligence, we can achieve individual tasks of whether it is automatic test generation or merge conflict resolution or code translation or code generation or code completion, all of that stuff we can do with very, very little work by fine tuning. So it has fundamentally changed the way we develop productivity software, the way we build intelligent products. Now, more recently, we have been able to combine all 3. We've been able to take language elements like grammars and flow graphs, etc., combine with that with clever use of data for training and retraining, as well as for fine-tuning, and combine them with the tasks that are driven by the AI models to achieve even better results. Of course, a lot of other work has to be done in order to get to the next level. Now, number one, we still talk about correctness. What does it mean to generate correct code or produce results that are acceptable to the user? How do we create systems that perform well without degrading, the user experience? And then there is this question about transparency of the models. How much do they know? How much do they learn? And how transparent are these models in explaining what they do? Then there's this constant concern about privacy and security. While we have taken several measures to make sure that user information or private information doesn't leak into these models, it's a constant challenge to make sure that it doesn't happen, or the models or the data doesn't get poisoned in a way that privacy or security is violated. And finally, there's this big question about fairness and bias. How good is this data so that it is fair across all the dimensions in which we use these models and we avoid bias. So with that, I want to thank you for your attention in this session and hope you enjoy the rest of the conference. Thank you.
Hello, everybody. My name is Oege Moor, and I am the VP of GitHub Next. GitHub Next is a group of researchers within GitHub who are exploring the frontiers of software engineering. One of those frontiers is the use of AI to make developers more productive. And I'm extremely grateful to the organizers and to you all here to give me the opportunity to talk about GitHub CoPilot, our most exciting project in this space. GitHub CoPilot is a collaboration between OpenAI and GitHub, and literally dozens of people have contributed. I would, however, like to acknowledge my two co-founders on the project, Alex Gravely and Albert Ziegler. And in particular, Albert's work will feature very much later in this talk. For those of you who haven't seen CoPilot before, I'd like to show you a little demo. In my spare time, I like to read about history, and often that involves reading old books in languages that I do not understand. So for example, on this slide, there's a page of a book about Zebuj, a little village in Malta. The book is in Italian, and I would like to read this page, but I don't understand Italian. So what I'm going to do is to write a little app that takes a picture like this, extracts the text in Italian, translates it into English, and then shows the original page with the translation next to it. So let's see how that works with CoPilot. I'm here in VS Code. I've already imported some libraries that might be useful. So let's try and write the code. First, we need to get the text. And I just said in English what I wanted to do in a command, convert the image to text in Italian. When I hit the return button, CoPilot responds in gray text with a complete implementation of this function. And if I like the implementation, which in this case I do, I just hit the tabbed key to accept it. Next, we actually need to translate that text. So let's write a function for that. Again, I just say what I wanted to do, translate the text into English. And once again, CoPilot responds with a complete implementation, which I accept by hitting the tab key. All right, so remember that I said that I actually want to create a new image where we've got the original image next to the translation. So we're now going to write a function for that. I'll call it juxtapose. It takes an image and it takes a text. And let's describe what it should do. Create a new image. Okay, so we want to create a new image with the original image on the left and the text on the right. Let's give a little bit more detail. We want to make the image twice the width of the original, but the same height. And finally, I'd like to display the text in white on a black background. So let's see what CoPilot makes of that. It does give me a complete implementation, which again, I accept. It doesn't actually know that I'm working on a MacBook today. And so the location for the font is not quite right. So let's change that. And I want it a little chunkier. It would also be nice to shift the text a little bit to the right. So let's add 30 to that width. Okay, so now we need to put it all together. Let's define a function process. It takes an image. And let's see, what should that do? CoPilot has already figured it out. We want to get the text, we want to translate it, and then juxtapose the image and the text in English. So we accept that. And now we want to try it out. Note that every time I just hit the return key and then tap to accept the lead that CoPilot gives me. So let's execute that. This is like going to the NASCAR races. We're now all waiting to see whether a crash will happen. It's almost right. It's almost right, but not quite. The text is actually running off the page, so we need to wrap it. Okay, that seems pretty good. It knows how to do that. So let's try that once again. And there you go. Exactly what I wanted. The original text on the left and the translation on the right. What you've seen is that CoPilot allows you to write this sort of thing without all those annoying web searches that take you out of the flow. You get the advice you need right inside your code editor. How does this actually work? As you saw, I was typing my code in the VS Code editor, and every few keystrokes, it sends the editor context to the GitHub CoPilot service. That does a little bit of processing, and then it asks the OpenAI Codex model what might come next to complete the code that the developer is currently working on. Suggestions come back from Codex. We cut them to size to make sure that they make syntactic sense at that point in the code, and then they're displayed in gray text. And as you could see, you hit the tab key to accept them. So currently, this is a new product. It's in preview, and we really want to learn how people are using it and how we can improve it. And so we're really grateful to everyone who joined the preview that they agreed to the telemetry terms. This gives us invaluable information, as we'll see shortly, in order to improve the UI, but also to improve the models and eventually the suggestions themselves. So what you've seen is that in some cases it works pretty well, but how good is it really? In order to answer that question, we created a test harness that you point at GitHub repositories, and the harness will find suitable target functions in the source code to give to the model to fill in. So a good target function is one that has good test coverage and also a reasonable doc strength, so we have something to go by. In this graph, on the left-hand side, the success rate indicates how often the model succeeded in creating a solution that passed the unit test. And on the horizontal axis are the number of shots, the number of attempts that the model got in order to get this right. Now, there's actually two lines. The red one is the model that we launched with all the way back in June, and the blue one is a new model that we recently deployed. And as you can see, it's massively better. It's correct much more often than the old one. And these are improvements that we see all the time. And it's because of that, because of these improvements, that I'm super optimistic that this is just the beginning. There's still so many more improvements that can be done. We are very confident that the model can get way better in synthesizing correct solutions. All right, Dr. De Moor, that is very nice. You've shown in a laboratory experiment that you can generate code that pass more unit tests. But what about your users? Do people actually benefit by having such an improved model? In order to answer that question, we did an A/B experiment. We gave half of our users the new model, and half of the users stayed on the old model. And then we looked at three metrics. The first of these metrics is just the suggestions per user hour. If you use this thing for an hour, how often do you accept a suggestion? And if you accepted a suggestion, how often do you retain it? So you don't make any edits. As you saw in the demo, it's not uncommon that you get a suggestion and then later you make a change. So we take it that if you left the suggestion alone for 30 seconds, that counts as a win. So after a suggestion is accepted, we look 30 seconds later, no edits. That counts as something that was retained verbatim. This is a good and simple metric, but sometimes we want to drill down a little bit deeper. And for that, we look at the funnel shape. The funnel shape of how many completions were requested, how many then were shown, how many of the shown ones were accepted, and how many of the accepted ones were retained. So you go see these completions go through each of the stages. You might think, why would you request a completion and not show it? Well, these requests are issued spontaneously. We don't have the user explicitly ask for them, and so the user may be typing and they just continue typing, and then by the time a completion comes back, it's no longer useful to the user, and we don't actually show it. That is also the reason that there is a trade-off here, a trade-off between extremely powerful models that are highly accurate and less accurate models that answer fast enough to be useful to users who type at normal speed. And then finally, the third metric that we looked at is the % of code that is actually written by CoPilot. So you look at the total amount of code that was added in a new session, and we ask ourselves the question, how much of that for a typical Copilot user, how much of that was written by the model? This, we believe, is a pretty good true measure of the benefit. All right, so let's go through these. Let's go through the results. The suggestions per user hour when we look over all programming languages. Yep, just as we would hope, the accepted solutions go up by 10%. So that's similar to the improvement we saw for our passing unit tests. Very encouraging. Actually, even more interesting, the increase in the number of solutions that are kept verbatim is higher, 14% more than for the old model. So this is good. People actually like the solutions, look at them carefully, and decide they will do fine. The results differ per programming language, and Python from the very beginning has been our primary focus. So Python performance is already very good. It's a much higher baseline to start from, and it's because of that that the improvement is significant, but smaller than for the other languages. Only 4% more is accepted, and still, also here, even more, a larger percentage is kept verbatim. Okay, so when we drill down and look at the funnel shape, whoa, almost everything is getting better. More solutions are shown per request, more are accepted per shown, more are kept verbatim after acceptance. But the first metric is actually down. We are speculating here, but we think it may be because the users are trusting the model more, and so they actually pause and properly wait for a suggestion to be given to them. Okay, so now for the final metric. Percentage of code written by CoPilot. So if we want to give a percentage of the total amount of code written, we first have to define what the total amount of code written is. We're going to look at code that has changed at code churn, and we're only going to count additions. And the way we detect that is that we look at the prompts for consecutive requests. So as you're typing, every so often a new request is issued and sent to the model, which we see in our telemetry. And if the prompt became larger, there's more code than there was before, we count that as an addition. However, not if it changed too much. If it changes by more than 100 characters, you probably jumped around in a file, or you even went to a different file. So we don't believe that you typed that, so we don't count it. And we're also not interested in just the really small little edits. We only consider sessions where more than 500 characters are added. So that's the definition of the total amount of code that was written in a session. We then measure the CoPilot contributions as the length of the contributions, minus the number of changes that you make to them. Unless you make too many changes, if you change more than half of the suggestion, we count it as a total loss. There, CoPilot didn't contribute anything. Arguably, it contributed negatively. So we only count contributions where the edits are fairly minor, less than half of the characters. So here are the results. Even the old model is actually quite a high number for Python, for all languages. 16.3% of the code is written by the artificial intelligence. And for the new model, it's even more, 19%. So this is very encouraging. Well, when I first saw this graph, what I found even more encouraging is that both lines are going up. Both lines, so we're running an A/B experiment during the same time period. And of course, both models are using the same UI. And so what you see here reflected in that increase in acceptances is that the user experience improved. We're a little bit more careful about debouncing. We were a little bit more careful about making certain UI elements discoverable. This has quite a big impact on the number of, on the amount of code that was accepted. So here is another way of looking at the data. For languages that are not Python, we have a 3% increase between the old model and the new model. And it's a large amount, 18%. But then look at Python. It was 27%, and now it's 29%, almost a third of the amount of code that people write when they're using CoPilot with Python. Almost a third is written by the AI. I find that very exciting, very encouraging, but it's only the beginning. We expect many more improvements like this. So we're very confident that that number will be way higher, even in a year's time. Okay, let me conclude. I've shown you GitHub CoPilot. I show you a little demo, and we've looked at different ways of evaluating how good CoPilot really is. We looked at the harness, which is really about how many unit tests can be passed by the model. So it's very much about program correctness. We then used that user metrics, looked at user metrics, and fortunately, those are pretty well correlated. Our users are quite discriminating. They accept more solutions if they are of higher quality. It's only the beginning, though, and we very much would like to hear your feedback, both on the whole idea of CoPilot itself, but also on these methods of evaluating how good the models are and how well CoPilot is doing, how helpful it is to its users. So far, CoPilot has only been used, we've only used the technology to help you create new code. But we think that the same technology can be hugely helpful in almost every other aspect of software development. In code review, in refactoring, in testing. So stay tuned for more announcements on those topics. That's all I had to say today. Thank you very much. I look forward to the discussions and feedback. Thank you.
Okay, thanks everybody for coming. So I'm going to talk today about this pesky little problem that happens when you do a git pull and you have made changes to some piece of source code that someone else has as well. And we're going to talk a little bit about how we use both machine learning and programming languages in order to come up with safe program merges. So before we dive in, I want to give you go through a little bit of trivia, get people warmed up here. So you can answer at home. I know this is a recording. A group of fish is called a school. Okay, another one. A group of kittens is called a litter. Okay, so now the tough one, now that we're warmed up. A group of software engineers is called a merge conflict. Okay, So a merge conflict is a drag on collaborative software development, right? It's happening all the time. And how a merge conflict arises is that we have some common base program that two people, call them A and B, have decided to edit. They both make independent changes, and then ultimately they need to merge their changes back into the mainline. Now, when they do that, one of the two, A or B, will have to if they've edited the same file, will have to do a merge conflict resolution. Right? They'll basically have to fix any conflict that arises between editing the same file. So what's pesky about merge conflicts is that you can have a situation where if you have continuous integration tests in your development cycle, base A and B respectively can all pass your continuous integration tests. But when you do a merge, even if it's a silent merge, which is handled automatically for you by tooling like Git merge, the continuous integration tests can fail. So merge conflicts are a major productivity drain on developers, right? So basically there are many studies that have shown this. One of them is on this slide here. Basically 10 to 20% of all merges have conflicts in collaborative software development projects. The thing with merges is that particularly when they get large is they're not always straightforward in how to do the resolution. And as a consequence, developers oftentimes delay merging those things for hours to days, which slows down the development cycle. Likewise, if they're very complex, sometimes developers will actually throw out the changes that either they or the other person has made, sync up later on with the teammate who did those changes, and then re-implement them after throwing out that work. So there's reproduction of work. So my colleague Shvendu Lahiri has a very nice blog post recently on safe program merges at scale. And he talks a little bit about this as a grand challenge for program repair research. I encourage you to go take a look at that. And the rest of this talk is kind of modeled after this very nice blog. So what is a safe three-way merge? Well, there's been a bunch of work on this in the academic community. Most recently, there was a great paper in Uppsala by Sousa, Dillig, and Lahiri, where they formally verified what it means to be safe in the context of a three-way merge. And I'll send you off to that paper to read it to get a deeper understanding, but I'll give you an intuition. The intuition is that any test that passes in A or B should also pass in that resulting merged program, right? So this is a very nice way to view the formal verification of a merge from a programming languages standpoint, because you don't have to worry about formally verifying A and having a spec for A, right? It's a relativistic view of safety. And so that gets you a huge amount of leeway in actually how they formally verify these programs. Now, despite this really great work, it's very difficult to apply it at scale. So there's been a bunch of work that is inspired by the programming language community that has tried to make a safe three-way merge, or at least partially toward a safe three-way merge. So there's an approach called structured merge, where what people do in this world is they lift the merge from working on lines of code, or list structured merge, in other words, to operating on AST elements. And the observation with this is that once you've done that lifting, a large number of conflicts can be safely merged by taking advantage of properties of those ASTs. So concretely, if you have two Java method declarations, you know that you can reorder them without causing any kind of a correctness issue. So the problem with these approaches, while they're great, is that they're difficult to scale, right? If you come up with if you want to do this for a new language, you have to go out and then build up the AST representation and build algorithms then on top of those, difficult to implement algorithms on top of those ASTs. And despite the fact that they do make some inroads into safety of the resulting merges they provide, they're not guaranteed to be safe on all merges. So some of my colleagues and I have been working for a while now on a machine learning inspired approach to a three-way merge. And we call this a data-driven approach, where we go off and we mine programmer actions. So we go off to Git and we find places where people do a resolution. We extract a big data set, and then we teach a model using machine learning to merge two programs. And now one of the great things that came out of this work, and actually is a necessity to make it work at all, was that we need to use some of the ideas from safe program merge that was in that original Uppsala paper in order to filter and produce a high quality data set, right? We have to throw out a lot of instances where the developer potentially didn't do a safe three-way merge. And by using those insights, we can get a very high quality data set. And thus then our models, once we've trained on them, are empirically likely to produce a safe result. So the nice thing about this is that they're easy to scale, right? If I come up with a new language that I want to apply this approach to, I go off and I just have to get data and train a model. The downside is that it's a list structured merge, and despite the empirical guarantees, it definitely does not give us any formal guarantee of safety. So I want to go into a little bit of detail about how MergeBERT works. So MergeBird is built, the architecture of MergeBird is built off of a very key observation that we made and other people have made as well in the literature, which is that most merges, when you actually look at them, they don't insert new tokens. It's mostly a reordering of existing tokens instead. And by tokens, I mean tokens in the actual programming language. So if we take a look at the pane on the left-hand side here, it's a line level conflict. That's what you would get if you ran git merge. So there's O with .js, which is the original common ancestor, and then A and B have both made edits. Now you'll see that both A and B changed the 10 to 11, except B also added an extra parameter to the max argument function Z. So if you look at this at the token level and just do a line structured three-way merge, you'll get that representation in the middle pane, where now it's very clear where the conflict is arising. Now what MergeBird does is it actually builds a classification engine on top of a finite set of actions to pick which action at a token level conflict should we take in order to produce a resolved merge on the right-hand side. Now, in this case, it's simple. The model just predicts take B, take the edit from B, because it subsumes the edit from A. And so MergeBird in the paper will show you, as we show, we have a finite set of actions. And so we've turned this rather complex problem into a classification task in order to produce the pane on the right. So that's the architecture of how MergeBird works. If we take a look at how MergeBird works in practice, we looked at 25,000 Java programs and merges and 16,000 JavaScript merges. JDime operates on Java. And if you look at the precision recall in F1, you can see that MergeBird on Java is significantly better in all three. So very concretely, if you look at precision, which is a function of how many times the tooling produced a suggestion, how accurate was it when it produced that suggestion, MergeBird for both Java and JavaScript is over 70% accurate, while the existing structured approaches are significantly less. So with that, I think we've learned a lot in trying to produce safe program merges, and we're not there yet, to going back to the blog post that Shivendu has put together. One of the things that we really want to think about is how do we guarantee safe merges at a massive scale, right? We believe there's some combination of machine learning and programming languages that has to come together in order to make this happen. But we're not there yet. And one of the very concrete metrics we'd like to throw out to the community is to think about what does it take to safely and automatically merge millions of programs. Along the way, we're going to have to solve a lot of very hard technical problems. One of which is, and I think a lot of AI for Code's tooling will have this problem, right? As we generate these models, which can produce larger and larger amounts of code, I think there's a very interesting UI experience that we need to think very hard about that lets us think about why, how do we present these code suggestions to users so that they can actually understand them in a reasonable amount of time, right? It's somewhat easy if a merge resolution tool produces a 2-line resolution, the developer can very quickly eyeball that and understand why the model made the choices it did or what the resulting code is doing. If that turns out to be 100 lines of code, it becomes much harder. And so having some sort of amount of provenance or understanding in the UI experience itself about what the model did and why it made its choices is going to be paramount to getting the developers to take these tools. So with that, I'd like to thank my collaborators. There's a whole host of people here who worked both within Microsoft as well as outside. We've had a great set of interns that have helped drive this work to where it's at. If you're interested in coming and working with us to understand how programming language research and machine learning research can help solve these very hard software engineering problems, please don't hesitate to send us an email. Thanks so much.